So today we are going to study work for open system. Okay, work done by open system. Okay, likewise we have done the work done by closed system for every processes. Okay, like adiabatic, constant pressure, constant volume, isothermal, polytropic. For every process we will find out the work done in open system. Previously we have done all these cases for closed system. Now we are going to do for open system. Before that we need to know something. Okay, now in the open system we have derived an equation as an equation for open system, steady flow energy equation for open system. Now that equation is known as steady flow energy equation, or simply SFEE equation. If anywhere you find the SFEE equation, then this is the equation you need to remind instantly. Okay, this is the equation. Okay, now if we say that we need to find out the energy equation, steady flow energy equation or SFEE equation, neglecting the kinetic energy and potential energy. Okay, if you see, neglecting KE and PE, what will be done? This will be nothing but the equation will be same, just the potential kinetic energy term and potential energy term will get cancelled. Okay, these terms will get cancelled. Now the final equation will come out as m dot into h1 plus these two are going to be neglected, plus q equals to m dot into h2 plus w. Now this is the equation of steady flow energy equation. Okay, this is steady flow energy equation when kinetic energy and the potential energy is getting neglected, then this is the equation we need to remember. Okay, and this one is the steady flow energy equation originally. Okay, without any conditions applied. Only condition is it is steady flow. Steady flow means what? Steady flow means the properties of any open system is not going to change with respect to time. Okay, the energy, that means the mass accumulated inside it is not going to change with respect to time. The energy accumulated inside it is not going to change with respect to time. Similarly, all the properties which are going to be there must not change themselves with respect to time. As the time passes by, these properties must not change. Okay, now this is the steady flow energy equation, and this equation would be very important for solving the questions from different devices or different open system problems. Likewise, we have analyzed some of the cases like turbines, compressors, throttling devices, etc. we have shown here. Okay, likewise we need to remember this complete equation for solving the questions which you are going to get in future. Okay, now these type of problems are very important. We'll solve some of the questions here. Okay, okay, so now we are going to study the steady flow energy equation for multi-stream flow. Okay, in the previous cases what we have done, we have seen through one of the stream the water or any fluid was coming in, and through another stream the fluid or the water which we have considered was going out. Now we have taken 2 for every cases. It can be 3 or 4, but for simplicity we have just considered 2 to understand the multi-stream flow. So this will be nothing but similar to the previous case only. What was done in the previous case? In the previous case we have taken out the in the left side we have taken all the properties in the inlet, okay, plus the heat, and in the right hand side of the equal to sign, in the right hand side we have taken all the properties of outlet plus the work which we are going to get, that is the shaft work which we are going to get from the open system. Okay, similarly from here only, similarly in this case also the inlet cases are 1 and 2 and the outlet cases are 3 and 4. Okay, so what are the inlet properties? Inlet properties will be whatever the properties are there for 1 and 2. Okay, so we have taken written down the same in the left hand side. This is the equal sign, and this is the left hand side, and this is the right hand side. Okay, in the left hand side we have written down m dot 1, that is whatever will be the mass flow rate through this passage, okay, through this passage. So m dot 1 into h1 plus v1 square by 2000 plus z1 g by 1000. Okay, that means whatever the mass is going to be there for m1, h1 is whatever is the enthalpy of that fluid which is coming in through this passage is h1, v1 square is whatever the velocity is, z1 is whatever the height from the datum of this passage. Similarly, all the values will be corresponding for section 2. For section 2, this is also going to be inlet properties, so this will also come in the left hand side of the equal side. So m2 dot into h2 plus v1, sorry, this is wrong, this is v2 and z2, v2 square by 2000 plus z2 g by 1000. Okay, and the heat, whichever the heat transfer will be there, we will write it in the left hand side. Like the previous case, we have written down the inlet properties plus the heat transfer. Similarly, here also we will write the heat transfer in the left hand side. In the right hand side, we are considering all the exit positions, okay, or the outlet cases. So outlet cases there are section 3 and section 4. Okay, the outlet cases there are section 3 and section 4. This is section 1, section 2, and this is section 3 and section 4. Okay, so in the outlet case, this will be m3 into h3 plus v1 square, sorry, this is also going to be 3 and this is also 3, 6, 4, 6, 4. Okay, so this will be m3 dot into h3 plus v3 square by 2000 plus z3 g by 1000. Okay, so, and another outlet case is at section 4. So section 4 would be m dot 4 into h4 plus v4 square by 2000 plus z4 g by 1000. So this will be the case of multi-stream flow. Okay, now again for we need to do the mass balance. So for mass balance, what will happen? The mass accumulated here would be 0. Why? Because the steady flow is what? Steady flow is the property is not going to change with respect to time, and mass is a property, so mass is not going to change with respect to time. That means the whatever the mass is there will be same. That means the mass accumulation is going to be 0. Okay, mass accumulation is going to be 0. That means this, if we consider the mass balance, what will happen? The mass accumulation is going to be 0. That means whatever the mass is going into through the entrance, okay, through the inlet, same amount of mass will come out of the outlet. Now if we consider the mass balance, what will happen? Accumulation is going to be 0. Okay, that means what? D mass is going to be 0. Okay, D mass, that is change in mass, is going to be 0. So what would be the accumulation equation? Accumulation would be whatever it is, whatever the water or fluid whichever we are going to consider, whatever it is entering minus the outlet is going to be 0. Okay, so at the entrance it is m1 dot plus m2 dot. Okay, minus, if we subtract the amount or mass whichever is going out of the system through the outlet, then we will get the mass accumulated. Okay, so if we subtract the mass whichever is going into the system through the inlet and we subtract it from this, okay, if we subtract the whatever the mass is coming out of the open system, okay, if we subtract both these two, then the mass accumulation must be 0. So from this, what we can get that m1 dot plus m2 dot is going to be same as m3 dot plus m4 dot. Okay, so this is same, but the one condition is there. The condition is the flow must be steady. Okay, just because it is steady, it means the mass accumulation, or mass is a property, the mass property of the system is not going to change with respect to time. So the condition will be like this. This is the condition for steady flow equation, that is the mass accumulated will be 0. Okay, entering minus going out will give us the mass accumulation, which is going to be 0. So this is the final condition. Okay, okay, so now we are going to read about open system reversible work. Okay, we have already read about closed system reversible work, and we have discussed every possibility of the closed system. Okay, like adiabatic, isothermal, and all the processes we have discussed for closed system, closed reversible system. Okay, now while discussing that, we have said that what is work done in a reversible closed system. Work done in a reversible closed system was the area under the curve while projected on volume axis. Okay, if this is a PV diagram, while we take the area projected on volume axis, then that area gives us the work done in closed system reversible. Okay, reversible closed system. Any process which is reversible and it is closed system, that area used to, the value of that area used to give us the work done. Okay, but in open system, what happens? In open system, it is the reverse. Reverse means what? If you project the area, if the area under the curve is projected on pressure axis, then that value will give us the work done in reversible open system. Okay, while if you project it on volume axis, then it will give us the work done in closed system, which is reversible. But for open system, it is area under the curve while projected on pressure axis. Okay, if you project the area under this curve, if project it on pressure axis, then it will give us the work done in open system. Okay, so for finding out this, if we take a small strip, okay, it's basic integration. If we take a small strip which is having a breadth of dp and a length of volume v, okay, then that area of that small strip is going to be v into dp. To find the total area, what we'll have to do, we will have to integrate it from 1 to 2. From 1 to 2, if we integrate it, then this small strip of that small strip of area will give us the complete area from 1 to 2, which will be projected on pressure axis, and that area in pressure axis while projected on pressure axis will give us the work done in open system. Okay, that is area under the curve while projected on pressure axis gives open system reversible work, and it is the negative integration. Okay, negative integration of VdP from 1 to 2 is the open system work in general condition. Okay, now based on this, we are going to discuss it for various processes. Okay, okay, so the next thing we are going to, I mean the first case now we are going to discuss under the open system reversible work is constant pressure process. Okay, now another question you may be having in your mind, that why W open is taken as negative. Okay, we have taken negative, and there also we have taken it negative because in the steady flow energy equation, SFEE equation, whatever we have found out the work that we have given, that is in the right hand side, whatever W was given, we have considered that W as work done on the system. Okay, that is the reason why we have taken W as negative. Okay, now that is one thing. Now constant pressure process. Now for constant pressure process, this is the general equation by using which we are going to find out the work done in case of constant pressure in open system reversible. Okay, now since pressure is constant, dp is going to be 0. dp is going to be 0, that means this part is going to be 0. Okay, this part is going to be 0, that's why W open is also going to be 0. Now if we come to PV diagram, what happens? A constant pressure process is generally a straight line which is perpendicular to pressure axis or parallel to volume axis. Okay, now this is a straight line. If you project this straight line on pressure axis, what will you get? You will get just a point. Okay, and area of that point is going to be 0. Okay, that means what? If you project a line, if you project a constant pressure process in pressure axis, you will just get a point, and area of a point is always 0. Okay, that's why by using these two methods we can say that work done in an open system while it is constant pressure, the work done is going to be 0. Okay, okay, so the next thing we are going to discuss is constant volume process. Okay, to find out the work done in open system, the next topic is constant volume process. Now again the equation is going to be same, W open equals to minus of V into dp. Okay, now here what is there? V is equals to constant. Now if V is equals to constant, then what W will be negative of V is constant, so V will come out of the integration. V will come out of the integration and negative sign is there. Okay, and if you do the integration of dp from 1 to 2, what will you get? You will get p2 minus p1. Okay, this is going to be your work done in open system for constant volume process. Okay, now if you multiply this negative with the terms within the bracket, then you will get v into p1 minus p2. Okay, v in w open. Now w open for constant volume process. W open for constant volume process for an open system is going to be v into p1 minus p2. Okay, now if you come to PV diagram, in PV diagram what happens? If you draw a constant volume process, it is something like this. Okay, if you draw a constant volume process, it will be perpendicular to the volume axis and it will be parallel to the pressure axis. Okay, in each and every point it will be having the velocity, it will be having the volume, whatever the volume is at this point. Okay, so this is a constant volume process while you plot it on a PV diagram. Okay, now if you consider according to the area projected, what we have said? We have said that for open system reversible work, whenever you project the curve on pressure axis, whenever you project the curve on pressure axis, whatever area you are going to get, that area will give us the work done on open system. Okay, so what happens if you project it on pressure axis? Suppose this line is going to have a velocity of v. Okay, velocity of v, and at this point, in this suppose this is 1 and this is 2. Okay, now suppose at this point the pressure is p1 and at this point the pressure is p2. Okay, so what will be the area? Area will be nothing but this is length into breadth. Okay, length is what? It is volume v. Okay, it is volume v. This is the length, and breadth is what? It is p1 minus p2 will give us the breadth. This is from here to here. The value will be p1 minus p2. Okay, so length is v and breadth is p1 minus p2. Now this area is going to give us the work done. Okay, similarly here this is the length and p1 minus p2 is going to give us the breadth. So if you plot it on this, the same expression will be there. That will be v into p1 minus p2. This is for completely constant volume open system reversible process. Okay. Okay, so the next thing we are going to discuss is isothermal process. Okay, isothermal process, that means this is the third case. Okay, third case, isothermal process. We are going to find out what is going to be the work done in open system while the process is isothermal. Okay, now again the equation is going to be same. This equation is going to be same. W open is equals to minus of 1 to 2 v into dp. Now in isothermal process, we have discussed earlier the isothermal process. The ideal gas equation for isothermal process is PV is constant. Okay, PV is going to be constant. Okay, that means from this equation PV is going to be constant. From this equation we can write that volume is equals to C by P. Okay, we can write that volume is equals to C by P. Now if you rewrite this equation here, what will you get? You will get from 1 to 2, in place of V we can replace it by C by P. Okay, we can replace this by C by P into dP. Okay, same equation we have written down here. We have just replaced V with this V. Okay, now since C is constant, C will come out of the integration, and inside the integration it will be 1 to 2 dP by P. Okay, now the value of C is what? Value of C is nothing but P into V. Now P into V is equals to constant. We can write it as P1 V1 equals to P2 V2. That means the product of P and V is always going to be constant. So at point 1 we are taking the product of pressure and volume. At point 2 we are going to take the product of pressure and volume. Now these two are going to be same. So in place of C we can write whatever it is, P1 V1 or P2 V2. I am writing minus of P1 V1. Okay, you can also write P2 V2 because this these are going to be same. Now dp by p gives a derivation, that is dp by p, integration of dp by p gives us ln natural log of p2 by p1. Okay, this will give us the natural log of p2 by p1. Now negative sign is there. If you want to withdraw this negative sign, only the reciprocal of this will be remaining. Okay, that means if you take this minus, there is a rule for log, natural log or log. What is it? If something is in product, you can take it as the power of this one. Okay, you can take this as the power. Now if you take minus, you can write this as minus as this to the power minus 1. Okay, this to the power minus 1. So in the next line it will be changed as p1 v1 into ln p1 by p2. Okay, this is going to be the expression for W open in case of open system reversible process for isothermal process. Okay, now P1 by P2, from this equation we can write P1 by P2 is equals to V2 by V1 we can write. Now if you replace this here, you can write it as P1 into V1 ln V2 by V1. That means P1 V1 ln final volume by initial volume. Now if you remember, while using the closed system, while deriving the closed system work for isothermal process, we had also got P1 V1 final volume by initial volume. So W open is going to be same as W closed in case of isothermal process. Okay, that means what? For isothermal process, whatever work done expression you are getting for open system, the same expression will be there for closed. Okay, so in isothermal process, W open is going to be same as W closed. Okay. Okay, so the next thing is adiabatic process. Okay, that means we need to find the work done in adiabatic process for open system, which is reversible. Okay, now we all know that ideal gas equation for adiabatic process is PV to the power gamma equals to constant. We have derived it also, that PV to the power gamma is constant. Okay, now from here we can write that V is equals to C by P into C by P to the power 1 by gamma. Okay, now this is the work done expression for open system. We are discussing it for 2-3 processes now. That minus 1 to 2 V into dP. Now again this V is replaced by C by P to the power 1 by gamma. Okay, we have replaced this V with this V. Okay, now from here what happens? The C to the power 1 by gamma is constant, so we are taking out C to the power 1 by gamma. Negative sign is already there. C to the power 1 by gamma is constant, so we are taking out this. Now inside the integration, what is remaining? 1 by P to the power 1 by gamma is remaining. Okay, which we have written here in dP. Now P to the power 1 by gamma, which is 1 by P to the power 1 by gamma can be written as P to the power minus 1 by gamma. Okay, now if you integrate this, what happens? Now if you see, if in an integration there is a term like x to the power n, integration of x to the power n, then it is written as x to the power n plus 1 by n plus 1. Okay, now here P to the power minus 1 by gamma. Okay, so this will be written as this one. Okay, minus C into 1 by gamma, and according to this formula, the integration will be like this, which will be from point 1 to 2. And if we substitute this point 1 and 2, this is going to be the expression. Okay, this is going to be the expression. Now we have kept it C here. Okay, we have kept it C here. Now I am erasing this one. Okay, now what happens? You can see that PV to the power gamma is constant. PV to the power gamma is constant. That means what? From this equation we can write that P1 V1 to the power gamma equals to P2 V2 to the power gamma equals to constant. Okay, we can write. Okay, now if you substitute, if you multiply this gamma minus 1, if you multiply C to the power gamma, okay, C to the power 1 by gamma with all of this, what will you get? C to the power 1 by gamma into P2 to the power gamma minus 1 by gamma. One negative sign is there, okay? One negative sign is there. C to the power 1 by gamma into P2 to the power gamma minus 1 by gamma minus P1 into gamma minus 1 by gamma into C to the power 1 by gamma. Okay, we can write it like this. Now what is the value of C? Now since it is P2, we will substitute this C as P2 V2 to the power gamma. Okay, and as this C is with P1, we will substitute this C as P1 V1 to the power gamma. Okay, for our simplicity. Okay, now what happens? This will be written as W open will be written as after this line. Okay, I am coming directly here. So what will happen? This will be minus gamma to the power gamma minus 1 minus gamma to the power gamma minus 1. C1 we are replacing by P1, sorry, P2 V2 to the power gamma whole to the power 1 by gamma. This value is C. Okay, this part is C and to the power 1 by gamma into P2 into gamma minus 1 by gamma, and if you substitute this, then P1 to the power gamma minus 1 by gamma into, now this is P1, so we are replacing C with P1 V1 to the power gamma. So P1 V1 to the power gamma whole to the power gamma minus 1 by gamma. Okay, now this gamma and this gamma will be cancelled. This gamma and this gamma will be cancelled. So whatever this is remaining is gamma minus 1 into P2 to the power 1 by gamma. Okay, P2 to the power 1 by gamma, and V2 to the power gamma gamma is going to cancel, so only V2 will remain into P2 to the power gamma minus 1 by gamma. Okay, minus again similarly P1 into 1 by gamma into V1 into P1 to the power gamma minus 1 by gamma. Okay, now if you add this is power, okay, this is power gamma minus 1 by gamma. Now P2 to the power 1 by gamma into P2 to the power gamma minus 1 by gamma. If you multiply this, you will get P1. Okay, if you add this, that means P2 into P2, their powers will be going to get added. If you add their powers, you will get only P1. Okay, now if we simplify this, the final thing which we are going to get is gamma to the power gamma minus 1. Okay, the next I am skipping only one line. Okay, this one line will be P2 whole to the power this power plus this power. Okay, simply indices. In indices, what happens? If x to the power 1 in x to the power 1 into x to the power 3 is there, then what we do? We do x to the power 1 plus 3. Similarly, P2 and P2 is there. You will just need to add these powers. Okay, just need to add these powers. If you add this power, you will get P1. Okay, so the final expression which we are going to get is gamma to the power gamma minus 1 into P1 minus P2. Here it is P2 minus P1, but negative sign is there. We are multiplying this negative sign, so we will get, sorry, P1 V1 minus P2 V2. Okay, I'll write it clearly, because V2 is nothing. V2 is going to be same and V1 is also going to be same. So V1 and V2 are going to be there, but P1 and P2 are going to become, that means these two powers will combine them to become P2 and P1. So if we multiply this minus also, the final expression we will get P1 V1 minus P2 into V2. Okay, so this is going to be the expression for adiabatic process while it is open system reversible. Okay, now in the same way we can say that if it is replaced by polytropic process, what happens? This is polytropic process. What happens? In place of adiabatic, this is Pb to the power gamma is constant, but in case of polytropic process, it is Pb to the power n is constant. Okay, in every place if we replace gamma by n, we will get the expression for polytropic process. Okay, so each and every case if we replace this by replace gamma by n, we'll get the expression for polytropic. Similarly, if you remove all these gamma and replace it with n, the final expression for work done in polytropic process is going to be n by n minus 1 into P1 V1 minus P2 V2. Okay, all the derivation is going to be same for polytropic process, but in case of gamma, n will be there. Okay, and we all know n value is less than gamma and greater than 1. Okay, if we remember these expressions, okay, this is going to give us the polytropic process expression for work done, and in place, if we replace n by gamma, it will give us the expression for adiabatic process. Okay, in case of open system and reversible. Okay. Okay, so now we are going to see unsteady open flow system. Okay, unsteady open flow system means what? The properties of that system is going to change with respect to time. In case of steady flow, earlier we have studied all the cases of steady flow. In steady flow, what happens? None of the property was changing with respect to time. Now properties are going to change with respect to time, so we are going to consider unsteady system. Although in all the theoretical parts most of the cases are steady flow only, but there are certain exceptional examples which is required for gate point of view, and for this we need to study unsteady flow system. For example, suppose they have given that there is a pipe, and with that pipe, there is an evacuated tank they have given. Okay, and there is a valve. Okay, one valve is given, and this is an evacuated tank. This is complete vacuum, and this is, if through this some fluid is flowing. Suppose air or liquid, whatever there is, some fluid is moving. Now suppose we have opened this valve. So after opening this valve, what will happen? Some of the fluids or whatever the materials is flowing through this pipe will come into this tank. Okay, which was previously evacuated is now filled with whatever fluid is flowing through the pipe. Okay, now what happens if we consider this as a system, if we consider this thing as a system, what will happen? Initially the property, the mass is a property, so initially the mass inside the tank was 0. Now as the time passes, and if we are opening this valve, and as time passes, the mass is going to change with respect to time. Suppose time t, we are getting an amount of mass m inside this tank. Okay, now this is the example of a unsteady flow system. Okay, this means unsteady flow, unsteady open system. Open system, why? Because there is mass transfer is going on. Okay, at first we have studied 3 systems, no? Isolated, closed and open system. In open system there was mass transfer as well as energy transfer. So there is mass transfer is happening. Now this is an open system, and this is unsteady because properties like mass and energy is going to change with respect to time if we allow something to come in this evacuated tank. Okay, now this is one example. Similarly, considering these type of problems which you have seen, that we through one side fluid or air or something is coming, and through other side it is going out. Now in previous cases what I have seen, we have considered steady, okay, steady processes or steady flow process. For that, what was there? No mass accumulation was there. Okay, there was no mass accumulation, there was no energy accumulation, because if mass accumulation is there, that means mass was going to increase with respect to time. But since that was steady flow, the properties like mass and energy was not changing. That's why accumulation of energy or mass was 0. Now in such cases, accumulation of mass and energy is going to be there because this is unsteady. Okay, okay, so now let us see mass balance and energy balance in case of unsteady flow open system. Okay, now as I have said earlier, suppose here at section 1 and section 2 is there, and section 1 stands for inlet conditions and section 2 stands for outlet conditions. Okay, and now it is unsteady flow. Unsteady flow means the mass accumulation is going to be there. In case of steady flow, you might have remembered that mass at exit minus mass flow rate at exit minus mass flow rate at inlet was 0. Okay, because that was steady flow, and according to the steady flow the mass accumulation was 0. Now what happens, there is a, now as this is unsteady, there is one mass accumulation. Now let us, this is not going to be 0, so let us say that mass accumulation is dm by dt. Okay, that is accumulation of mass with respect to time for control volume CV. Okay, now this is going to be the mass balance equation. Initially this was 0, so that's why mass at inlet and mass at exit were same. Now difference of this is going to give some value. Okay, so now you can see, you can say that mass at inlet, okay, plus this one will give the mass at exit. Okay, this is going to be the mass balance. Okay, now in case of energy balance, what will happen? If you write energy balance also there will be some energy at energy balance. For energy balance there will be some mass energy accumulation inside the system. Okay, now for energy balance what will happen? There will be an accumulation of energy, that is, suppose change of energy with respect to time for control volume is going to be equal to EI or E exit, E energy at exit minus energy at inlet. If you subtract energy at exit minus energy at inlet, you will find the value of energy accumulation inside the system. Okay, now if you remember, energy at inlet as we have derived earlier was m dot at inlet into enthalpy at inlet plus velocity at inlet square by 2000 plus height of that entrance from the datum g divided by 1000 plus q was there. Okay, and energy at outlet, energy at exit or outlet, it was similarly mass flow rate at exit plus enthalpy at exit plus velocity at exit square by 2000 plus height of that entrance, height of that exit passage from the datum, that is ZEG by 1000 plus WCB, work done on the control volume. Okay, this is the energy balance. Okay, now you can say that dE by dt is this one minus this one. Okay, now as we know that energy of a system is, we have discussed this earlier in case of first law, energy of a system is consisting of three other energies: kinetic energy, potential energy and internal energy of a system. These three energies consist of the total energy of the system. Okay, now from these things, if you neglect the kinetic energy and potential energy, what will you get? You will just, if you neglect these two, you will get only the internal energy. Okay, now from this you can write that if you neglect Ke and potential energy, if you neglect kinetic energy and potential energy, you will get only change in internal energy with respect to time for control volume. Okay, this thing will turn into this. Okay, this thing will turn into this if you neglect kinetic energy and potential energy. Okay, now from this, if you again kinetic energy and potential energy is neglected, so velocity terms will be getting cancelled and height terms will be getting cancelled. Okay, now this is the condition, neglecting Ke and Pe. Neglecting Ke and Pe, this equation will now become as energy at exit minus energy at inlet. Okay, energy at exit remaining is m dot E into He, okay, plus W into CV, okay, minus energy at inlet. Energy at inlet is mass flow rate at inlet into enthalpy at inlet minus heat transfer. Okay, now for this one, for unsteady flow, this is the energy balance with by neglecting kinetic energy and potential energy. And if you do not neglect kinetic energy and potential energy, you can simply write dE by dt equals to this term minus this term, this term minus this term, because exit minus inlet. Okay, this term minus this term will give you the energy accumulation, and this term will give you the internal energy accumulation of the system. Okay, now this is the analysis of unsteady flow open system. Okay, so now let us do the analysis of mass balance and energy balance. Okay, as we have told earlier, since it is unsteady, there would be mass accumulation and energy accumulation in the system which we are going to consider. Okay, now let us suppose at the entrance we have given one section, that is 1 1, and at the exit we have given one section as 2 2. Okay, so 1 we are going to consider as inlet conditions, and with the terms with 2 we are going to consider as outlet conditions. Okay, now first of all let us see the mass balance. Okay, now in terms of steady flow, terms of steady flow, what was there? We have decided that, or we have done that in any system for a steady flow, that is energy is not going to change with respect to time, so mass accumulation was 0. So we had taken mass at inlet, mass flow rate at inlet minus mass flow rate at exit, or mass flow rate at exit was 0. Okay, it was in terms of steady flow. This is unsteady. I don't consider this as this is done under unsteady. I am just remembering the previous derivations which we have done. Okay, so mass flow rate at inlet minus mass flow rate at outlet was 0 for steady flow. For that reason, these both were equal. Okay, now what happens, as this is unsteady flow, some mass accumulation is going to be there. Let us suppose that mass accumulation is dm by dt, or change of mass with respect to time, for Cv. Okay, this will be the mass balance equation for unsteady flow, unsteady open flow system. Okay, suppose 5 kg of air, 5 kg per second air is going into the system. Okay, 5 kg per second air is going into the system, and through here 2 kg per second is going out. Then what is the mass accumulated per second? Per second there is 3 kg of mass, 3 kg per second there is 3 kg of mass accumulated. That is, for inlet I have said that 5 kg per second, and for outlet, okay, or exit, we have said that it is 2 kg per second. So mass accumulated would be 3 kg per second. This is the mass balance equation for unsteady flow in an open system. Okay, this is it. Similarly, there is energy balance. Okay, now if you consider that suppose there is some energy, fluid or air or something, whatever the material is going into the system, they are having a certain energy, and while they are going out they are having a certain other form of energy, or the energy they are having is having a lesser value. That means what? Some of the energy is getting stored into the system. Okay, some of the energy is getting stored into the system. Now if we consider energy balance, similarly for steady flow, what was there? Energy accumulation inside the system was 0. So at the time of steady flow, we have said that energy at inlet is going to be energy at outlet. As equating this, we have got one steady flow energy equation. If you remember, equating these two, energy at inlet, we have added all the energies at inlet, and we have added all the energies at outlet at the right hand side, and by simplifying that equation we had got one steady flow energy equation, if you remember. Now what happens? Now these two are not going to be 0. These two may be 0, but our consideration is unsteady flow. Unsteady flow is property is going to change with respect to time. Okay, property is going to change with respect. That means energy accumulation, energy of the system is also going to change with respect to time. If the energy of the system has to change with respect to time, some energy accumulation is required. that means energy at inlet minus energy at exit is going to have certain value. Okay, that value, let us say that dE by dt. Okay, change of energy with respect to time for that system. Okay, for control volume. Okay, this is the energy balance equation for unsteady flow for open system. Okay, now as if you remember, we have said that energy at inlet, for energy at inlet there was mass flow rate at inlet into enthalpy at inlet plus velocity at inlet square by 2000 plus height of the entrance from the datum, that is z inlet into g by 1000 plus q. Okay, heat transfer. Again, if you remember, energy at outlet or energy at exit, mass flow rate at exit. Now if you remember, in the steady flow case we have written both the terms as m dot and m dot, because for at mass balance m dot 1 and m dot 2 was similar. Okay, so that's the reason we had written m dot and m dot same. Now, but here it is unsteady, so mass flow rate is going to change. That's why we are writing different m here, mi dot, here me dot. Okay, plus enthalpy at exit plus velocity at exit square by 2000 plus height of the exit from the datum, z exit g by 1000 plus whatever the work done on the system was there, we had written. Okay, now if you see what will be the energy balance equation in terms of this, we can simply write that this one minus this one is going to be this one. Okay, now I am not going to write again, I am just showing it simply that suppose this is inlet, this is the energy at inlet. Okay, this is the energy at inlet minus this is the energy at outlet, is going to give you the change in energy with respect to time, or you can say that this is the energy accumulation per second into the system. Okay, in the system what is going to be the energy accumulation is given by this equation. Okay, now if you remember, in the first law of thermodynamics we have discussed that energy of a system is comprising of three other energies. Okay, one is kinetic energy, one is potential energy, and another one is internal energy. These three energies combinedly become the energy of a system. Okay, now if you consider another condition. Okay, if you consider another condition, suppose neglecting kinetic energy and potential energy. Okay, now if you see, if you neglect kinetic energy and potential energy, what will you get? You will only get the internal energy. Okay, now this is the condition, neglecting kinetic energy and potential energy. Okay, if you neglect kinetic energy and potential energy, this E is going to become only internal energy. Okay, this E is going to become only U, because P and E are going to get cancelled out since we are neglecting. Okay, now again from this equation, what are the terms which signifies the kinetic energy and potential energy? This term with velocity signifies the kinetic energy. So since it is neglected, this is going to become 0. This is also going to become 0, because this signifies potential energy. Okay, now these two are kinetic energy and potential energy at inlet. Similarly for exit also we are neglecting kinetic energy and potential energy. Okay, now this whole, under this condition, neglecting kinetic energy and potential energy, this equation becomes du by dt for control volume. Okay, this equation becomes du by dt, E becomes u. Okay, after cancelling this. Okay, and this equation becomes mi hi. Okay, since these two are getting cancelled out, we are neglecting this, and another one is plus q. Okay, and subtracting this one. Again, if you subtract this, what is remaining here? M dot E, mass flow rate at exit minus the W. whatever W is given here, okay, that is work done by the system or on the system, whatever it is, this W is going to be there. Okay, now this, after cancelling this one, this was the energy balance equation for unsteady flow open system. Now under this condition, neglecting kinetic energy and potential energy, this is going to be the energy balance equation for unsteady flow open system process. Okay, this is the mass balance and energy balance for unsteady flow. Okay, so now let us consider this special case. Okay, now air or fluid, something is flowing through this pipe, and this is an evacuated vessel. Okay, and it is completely insulated. Okay, evacuated vessel and completely insulated, that is this tank is consisting of total vacuum. Okay, and there is one valve. Okay, after opening this valve, what will happen, some of the mass will come into the this tank. Okay, or if we consider this as system, then some of the mass will interact into this system and some of the energy accumulation will also be there. Okay, now for such special cases, if you want to consider the mass balance, what will happen, you need to find the mass accumulation. Okay, that means change of mass with respect to time for control volume is going to be equal to, as we have discussed earlier, for open system unsteady flow, this is mass flow rate at inlet minus mass flow rate at exit. Okay, mass flow rate at inlet minus mass flow rate at exit. Now in this system, this is open system just because mass interaction is there. Okay, now in all other previous cases we have seen that for open system, one inlet is there and one exit is there, but here exit is not there. That means mass is coming into the system, but there is no way of going out of that mass out of the system. That means whatever the mass flow rate with which fluid or air is coming into the system is getting accumulated at same rate only, because there is no exit. As there is no exit, the mass flow accumulation rate of mass is same as that of inlet mass flow rate. Okay, these are going to be same. So this is one special case. And another thing is that if you want to consider energy balance, similarly energy balance, there is no exit. Okay, since there is no exit, that means change in energy with respect to time is going to be same as that of. Okay, so separately let us write what is going to be the energy accumulation rate equation. Okay, now neglecting the kinetic energy and potential energy, we have derived one formula in the last board that with neglecting kinetic energy and potential energy, dE by dt with respect to time is going to be mass at inlet into h at inlet plus q minus mass at exit into h at exit minus w. Okay, now as it is completely insulated, that means what, q is going to be 0, or heat transfer is going to be 0. Okay, since there is no exit, the exit conditions me into he is going to be 0, and since there is no shaft work, okay, w is also going to be 0. Okay, that means what, the energy accumulation rate in this system is going to be same as dE by dt into mi into hi. Okay, now as we have said that dE and dt, dE by dt. Okay, now in that case the potential energy and kinetic energy is neglected. So now if you neglect the kinetic energy and potential energy, it becomes internal energy. Internal energy by dt is equals to this mi into hi, and mi, as you have seen in the in mass balance case, of the same case, for the mass balance we have seen that mi was equal to what, mi was as same as dm by dt. Okay, for control volume, and this hi. Okay, mi for mass balance, what you have seen, mass balance was there, mi equals to dm by dt for control volume. Okay, now we have replaced mi by this. Okay, now that means what, rate of change of internal energy is going to be equal to rate of change of mass multiplied by energy at inlet for these cases. Now for general case, what will happen, for general case we can write this as, this means what, change of internal energy. Okay, that means u2 minus u1 for general. I am writing this for general case, and there is rate of change of mass. Okay, that means it will become m2 in m2 minus m1 into h1. Okay, this equation is going to be like this.